question 1 asks you to start with each of these 3 compounds and explain how you could turn it into 2-chloro-3-methyl-butane. So let's make sure we've got the right compound first of all. So butane means chain of 4 carbons, saturated, that's what the ane means, and 2-chloro we can put there, and 3-methyl would therefore be there. So that's the target compound that we are trying to make. So for each one we have to give the reagents, in other words what substances you add to each of these, the conditions, and also an equation which has to balance. Just because it's organic chemistry doesn't mean your equations don't have to balance. So that's got to be correct in each case. So for the first one, compound A, that's got to be radical substitution. That's the only thing you know that alkanes do. Okay, so it's got no functional groups there, it's just an alkane. So the only thing you can do other than burn it, which obviously wouldn't help, is radical substitution. And so the reaction you need is this plus chlorine gas will give you the compound you want, you hope, by just replacing a hydrogen from that carbon. That's a CH2, so there are 2 hydrogens. You could replace one of them with a chlorine to make that, and you would get HCl as the other product. And so that's your reagent, that's your equation, and the key condition is that radical substitution requires UV light. Now it's not a great reaction because substitution is random, so you could substitute a hydrogen there or there or there instead and get different products. So that's going to be kind of the point when we get onto it, but nevertheless it will give you some of the substance that you want. B, that's one of the standard reactions of alcohols that you need to know, that you can again do a substitution reaction, this time not a radical one, but a substitution reaction to replace that OH with a halogen. So we can do this. And what you react it with is a mixture of sodium chloride and concentrated sulfuric acid. Okay, so you have to learn this, that standard way of turning alcohols into haloalkanes requires the sodium halide, chloride or bromide, depending what you're trying to make, mixed with concentrated sulfuric acid. And you should specify concentrated. It doesn't work with lower concentrations of sulfuric acid. So that's the reagent. There are no special conditions other than that. Usually you might heat it, but that's not the main issue. The main thing is that combination of reagents. Now when you come to write the equation, effectively what it reacts with is HCl, because you're getting H plus from the acid and you're getting Cl minus from there. So what I've recommended in earlier answers and videos is that you write it like that, so that you remember that you get H plus from the acid and Cl minus from the sodium chloride. And that will give you your product, which is this. And the other product, we've got OH minus lost from here, which combines with the H plus lost from there to give you water. And that's a properly balanced equation. You know, you can check that out in the usual way. Alternatively, you could just write HCl there, and that would be fine. What you shouldn't do is write NaCl there, because to balance that up you'd have to then produce NaOH as the other product, and that doesn't make sense in the presence of conc sulfuric acid, because obviously they're going to react together. So you can't really have a product of NaOH if the whole thing is occurring in the presence of concentrated acid. So you wouldn't get the mark for that equation. So the thing to do is learn it, so that you don't have to agonize over it on the day. And that's always the way with organic reactions, that sometimes you can sort of puzzle stuff out, but often you'll get it wrong, and it just wastes a lot of time. So learn these reactions as you go along. Okay, the third one is more straightforward, because that's one of the standard alkene reactions. Remember, alkenes always react by adding things across there, and what you want to do to make this product is to add hydrogen to this end and chlorine to that end. So it's just going to react with HCl. No special conditions this time. So it literally is just react it with HCl and you would get your product. Okay, so that's part A. So part B is asking us for the atom economies of each of these reactions that you've written down. So first of all, you have to remember the definition, which is that atom economy is equal to the MR of the useful product or the desired product divided by the sum of the MR of all of the products times 100. Okay, so you need to remember that definition. So it's the MR of the thing you want, which in this case is your chloroalkane, divided by the sum of the MR of all of the products. So this plus whatever else is produced times 100. So we can just work that out for each of these equations relatively straightforwardly. So the MR of 2-chloro-3-methylbutane is 106.5. So the atom economy will be equal to 106.5 is your useful product MR divided by the sum of 106.5 plus the other stuff. HCl weighs in at 36.5. All that times 100, and that comes to 74.5%. So what that means is that 74.5% of the mass of the starting materials you put in actually ends up as the useful product, and that's why atom economy is a useful number, because it gives you a feeling for what fraction, expressed in terms of mass, what fraction of the stuff that you put into the reaction ends up as something useful. If we do the same thing for this one, again same product, so same MR on the top, 106.5 divided by 106.5 plus water's the other product, so just 18 this time, times 100, and that works out as 86.5%. So it's a higher atom economy because although you're still producing a waste product as well, it has a lower MR, and so it messes up your atom economy that much less. But this one is the winner, of course, because you only have one product, so the product is the useful product, and so the atom economy is 100% if there's only one product. In part C, it wants to know why we should care about atom economy. Why is it a good thing to have a high atom economy for an industrial process? So as I said, what atom economy tells you is what percentage of the mass of stuff you're feeding into the reaction actually ends up as useful product. And so there are really sort of two issues here. The first is that it's about making efficient use of those resources you put in. So high atom economy means that you're making efficient use of raw materials, and raw materials in this reaction will basically be petrochemicals, stuff that's been made from crude oil. And of course the crucial thing about crude oil is it's finite, it's going to run out one day, so we should use it wisely. We shouldn't just chuck it away unnecessarily. So high atom economy means efficient use of potentially finite, meaning they're going to run out one day, raw materials. Okay, so only a small amount of the input mass is wasted. So that's the first thing. The second thing is that it means what follows from that, obviously, is that the mass of other stuff that you get, the mass of the waste product that's produced, is kept small. And that's a good thing, because waste products have to be disposed of, and they have to be disposed of safely, and that can be problematic. So it means that you have minimal amount of waste product, which needs to be disposed of safely. Now obviously there are economic issues associated with this. You know, people doing industrial things don't want to spend more money than they need to on raw materials, and they don't want expensive problems of waste disposal to deal with. So there is a sort of financial aspect to this, but I think it's more important to sort of put your planet before your wallet and say, right, you know, this is good for the planet because we don't want to exhaust its resources quicker than necessary, and this is good for the planet because we don't want to fill it up with, you know, with polluting waste products. D is coming back to this issue that we mentioned earlier, that when we carry out a radical substitution on this reaction with the aim of making this product, which is our target, it's going to be very difficult to get a good yield of that, because a lot of the time the chlorine is going to substitute not for one of these two hydrogens, which is what you want it to do, but for one of these other hydrogens elsewhere in the molecule. And here it's just asking you, well, what other products could you possibly make? Now when you get questions like this, there are two things that you have to aim for. The first is not to miss out any of the possibilities, and the second is to make sure that you don't put any of them down twice. So in terms of making sure you get them all, the best thing to do is to be systematic. So if we start with our alkane, remember that that carbon framework won't change. So you can't write down products, you know, that are based on, say, that. If it's got the right number of carbons, it would have the right molecular formula if you put a chlorine on there, say, but you can't make it from that because the carbons don't rearrange in this reaction. So first thing to do, I think, to make sure you get these structures right, is copy down the alkane as a framework and then stick the chlorine onto it. A lot of people slip up by not doing it that way, just writing the structure straight down and missing out a carbon, or putting an extra carbon in, or putting the branch in the wrong place, or whatever. So good way to approach these is to say, right, all of these possibilities are going to be based on that alkane structure that we've got, because all we're doing is replacing a hydrogen with a chlorine. So in terms of exam technique, this is really important. If you lost marks here because you drew something that you thought looked right, but actually isn't, then this would probably be the way to make sure that doesn't happen another time. So you start by drawing that, and then you say, right, well, how many different ways can I put a chlorine on there? So one way you can do is to put it there instead, because there's a CH3 at the end. You could replace one of those hydrogens instead of one of those, and therefore that's a different product. So then you draw your alkane again. This one, that gives the desired product, so we don't need to draw that one down again. So what about this carbon? Well, it's only got 3 other carbons attached, so that one has a hydrogen, and that could be replaced. So if the chlorine goes on there instead of hydrogen, you're going to get this product. So that's your second one. Let's move along again. So we draw the same alkane down. So you can see now we've got 2 other carbons. But what you have to notice is that that's a CH3 and that's a CH3, and they're both bonded to the same atom. So if it substitutes there, it's exactly the same as if it substitutes there. It makes no difference to the structure, because these 2 methyl groups, as you rotate around this bond, they're just going to interchange anyway. So that's the danger, that if you draw 2 more products, one with the chlorine substituted here and one with the chlorine substituted there, then it's clear to the person looking at it that you haven't understood that those are just 2 different ways of drawing the same thing. Let's draw them both down so that you can see that that's the case. So if we substitute here, we would get this compound, and if we substitute up there, then we'd get this compound. But you can hopefully see that all we have to do is rotate around that bond there, and remember it's very easy to rotate around single bonds, and that will come down to here, and those two chlorines, those two carbons will change places. So that and that are the same thing. Okay, so that's why it's important to practice lots of these questions. First, well, three reasons. First is making sure you get the carbon framework right. We've talked about how to do that by drawing the alkane down first. Second, make sure you're systematic so you don't miss any of the possibilities out. But third, once you've drawn them down, check and make sure you haven't drawn any of them twice. So you need to edit this and say, right, well, we'll get rid of that last one because it's just the same thing. So there were actually three other compounds that you could get. And then the next bit it asked what was the term for the relationship between these compounds. And they're isomers, but more than that, they are structural isomers. Meaning that they have the same molecular formula, because they're all C5H11Cl, but a different structural formula, because the sequence of bonds is different. They're not stereoisomers, because stereoisomers have the same structural formula, meaning all the bonds are connected up in the same order. They just have a different spatial arrangement, but that's not what this is, so structural isomers. Part 3 wants us to talk about the consequences of this problem of the chlorine substituting at different positions. What are the consequences for the potential, for the percentage yield and for the atom economy? So percentage yield, remember, is equal to the actual moles produced of the particular compound you're trying to produce divided by the theoretical moles times 100. So if you remember, the equation that you wrote down for reaction A was this, plus Cl2 goes to the compound you want, which is that, plus HCl. So based on that equation, you would say, right, that's great. Theoretically, it tells you however many moles of this you've got at the beginning, you should get the same number of moles of your desired product, because each mole gets turned into that. Now we know that's not true because of these other possible reactions that could happen. So actually, each mole of this that you feed in, only a small fraction of this will do this reaction, because the rest of it will do one of the other possible reactions and make one of the other isomers. So that means that the actual moles of product will be much less than this equation would lead you to believe. So these questions, it's all about looking at the equation that's written down and saying, right, will you actually get as much as that equation suggests? And the answer is clearly no, because a lot of this will get converted into other things. So that number will therefore be small compared to theoretically what the equation predicts, and so the percentage yield will be low. Okay, so you just explain that the percentage yield is low because a substantial fraction of the amount of this compound that reacts gets converted to other products instead. What about the atom economy? Well, again, it just depends on the equation. And you look at the equation, and the equation says the atom economy is less than 100% because you produce the HCl as well. But these other reactions are neither here nor there. Atom economy is about when this particular reaction happens, how efficient is it? So you ignore other things that might go wrong. So the answer is the atom economy is the same, regardless of how big this problem of other reactions is. It's just saying that when this particular reaction happens, this is how efficiently it makes use of the mass. So atom economy is not affected by these competing reactions. Part E is pointing out that there are two possible alkanes you could use, which you could add HCl to and potentially make the product that we want, which remember is this. Because if we take this one, if we add H there and Cl to there, we'll get that. For this one, if we add H here and Cl to, sorry, other way around, H there and Cl to that, then again we'll get this product. And it's asking you which of these is going to be better. Now whenever you get questions about adding HCl or HBr or sometimes steam, HOH, to alkenes, and it's alluding to the idea of different possible products, you should be thinking about Markovnikov, about major and minor products being determined by the stability of the carbocation intermediates. It needs to be an absolute sort of conditioned reflex that you have as soon as you see questions about adding one of these asymmetrical things like HCl or HBr or steam to an alkene. It's probably going to be the issue that it's getting at. So let's just explore that. So remember that when this, let's do it for C first of all, when it reacts with HCl, the first thing that happens is H plus gets added. If you're not remembering this, look back at the mechanism of electrophilic addition. So what you would find is that you would get two possible carbocation intermediates, because if the H plus adds to this end, you'll get a positive charge there, and that gives you a secondary carbocation. Okay, secondary because the carbon with the positive charge has two other carbons attached. But if the H plus adds to here, then the positive charge will end up there instead, and then you'll get this, which is a primary carbocation. So these are alternatives. But then what we learnt was that the order of stability of carbocations is primary is the lowest. So these are the least stable, then secondary, and then tertiary, if you had one, would be even more stable. And the idea is the more stable the carbocation, the more easily it's formed. So what we'd say here is that this is more stable than the alternative one, which means it's more easily formed, which means that it leads to the major product. And the major product is going to be what you get when the Cl minus part of the HCl, remember the H plus is added on here, the Cl minus bit of it now adds onto there. And so this is going to be your major product with Cl minus adding onto there, and that gives you what you want. So your major product will be that, because that's what happens if the Cl minus adds onto there. So that is the desired product. And what we're saying is it's the major product, and in the language that we're using today, major product means high percentage yield. Okay, a big percentage of the molecules that react should end up giving you the right product. Okay, so that's high percentage yield. If we do the same thing for this, again, alternative carbocations. So if we add H to this end, H plus to this end, we'll get the positive charge there. So we'll get this intermediate. But if the H plus adds to here, we'll get the positive charge there, and we'll get this intermediate. So again, we compare the primary, secondary, tertiary thing. This one, the carbon with the positive charge has three other carbons attached. So that's a tertiary carbocation. Whereas this one, if the positive charge is there, well, that's the same one we made up here. This is a secondary one. So again, that means that this time this one is going to be the more stable one, because tertiary beats secondary. So this one is more stable, so more easily formed. So again, if it's more easily formed, it will lead to the major product, and the major product is going to be what you get when the Cl minus ion adds onto there where the positive charge is. So the major product this time will be this. And that's not the desired product. Okay, we wanted it to go onto the other one, but it's not going to do that. So that's not the desired product. And so that means that you'll get a low percentage yield of the desired product, because most of it is forming something else instead. So it's just a standard Markovnikov question, but with the added twist that you've got to use the language of percentage yield. So the major product means it's going to be formed in high percentage yield, at least unless there are other things going on that we haven't even thought about. But in terms of this competition, that's high percentage yield. If it's the minor product, you're bound to get a low percentage yield, so that's bad. There isn't anything to say about atom economy, because as we've said, the atom economy just depends on the individual equation you write for making whatever product you want, and so that's not affected by alternative competing reactions. Part F is a very important kind of question which comes up quite a lot in exams, where you have to make use of reactions that have distinctive observations to distinguish between various compounds, and you're used to doing this in inorganic chemistry, where you've learnt about ways to distinguish carbonates and sulfates and chlorides and bromides and so on using sort of simple test tube reactions, and this is asking you to basically do the same kind of thing, but this time use organic reactions that give distinctive observations. And it gave you a clue in this case, which was to be a bit more specific and say to use reactions that produce colour changes. So if you think about stuff we've learned, the obvious reaction that has a colour change is the bromine reaction, that when bromine reacts with a hydrocarbon, it gets decolorized, so it gets changed from orange to colourless. And if you remember the story, that if you have a saturated compound, which means either A or B, the only way that can happen is if you have UV light, so that you can get radical substitution. So if you had bromine in the dark, A and B can't react. No UV light, no radical substitution, and there's nothing they can do. But alkenes, remember, can undergo electrophilic addition. It's a completely different mechanism, doesn't need UV. So classic test for alkenes is that if you had bromine, aqueous bromine is what you normally use, in the dark, it will decolorize in the presence of an alkene, but not of a saturated compound. So that would be a possible way to start. So add aqueous bromine in the dark, and as we did with the inorganic ones, quite a good way to present these things is as a flow diagram. You don't have to do this, but it's quite a kind of clear and concise way of saying what your sequence of tests will be. So add aqueous bromine in the dark to each compound, just to a sample of each one, and if it decolorizes, that means that it must be C, because it's an alkene. So if there's no reaction, that means A or B, a saturated compound. Now, whether you do a flow diagram or not, what's important is that you do make it clear not just that C will cause it to decolorize, but that A and B won't. Okay, what people tend to do is they say, oh yeah, add bromine, C will decolorize it, and they don't say what A and B will do. And you think, well, it's obvious I'm implying, but implying doesn't work. You have to say explicitly no reaction. And if you do a flow diagram like this, that kind of happens naturally, so that's one of the advantages of doing it this way. So then what do you do? Well, what you do is you think of a reaction which this will do and that won't, because that's an alkene. Remember, alkanes don't really do very much. The only thing they do is radical substitution, but this has got plenty of CHs, so that can do radical substitution as well. So it's something that an alcohol will do that produces a colour change. So don't think of something like dehydrating it to make an alkene. Yes, it would react, but how would you know? You wouldn't see anything, or nothing obvious, certainly nothing coloured. So the one to think of is oxidation. Because remember, when you oxidize a primary or secondary alcohol with aqueous acidic potassium dichromate, it changes from orange to green. So that's a really, really useful test because it's a very dramatic colour change. So what you do is you heat with aqueous acidic potassium dichromate. If you're putting it in words rather than a diagram, you say you just do this for A and B. We're not bothering with C anymore because we know which one C is. Now the detail here is important. You have to heat it. If you just say add, it's not enough. It's got to be aqueous, it's got to be acidic. If you don't put those details in, it's not enough. Okay, so when you're learning this stuff, learn the whole package. Aqueous, acidic, potassium dichromate, and it always needs heat. You don't have to get into reflux and distillation and all that kind of stuff, because we're just doing this in a test tube to look for a colour change. So we're not trying to purify the product or anything, so you don't have to worry about reflux and distillation, just heat with aqueous, acidic, potassium dichromate. So two possible outcomes. If the solution goes from orange to green, that means that you had compound B, because B is a secondary alcohol, so it can be oxidized to a ketone. And if it's oxidized, the orange dichromate gets reduced to green chromium 3+. That's the origin of the colour. This can't react, so if there's no reaction, well, that's the one that's left. So that means it's A. Okay, and that answers the question. So you can see the diagram answers it very clearly without you having to write a huge amount. But however you choose to present it, those were the two tests. You could have done them in the other order, that would have been perfectly fine. But those are really the only two colour change tests that you've learnt in organic chemistry so far.